Thank you for giving me the opportunity to talk with you about neuroimaging of self-regulatory control in children with Tourette syndrome and ADHD. I would like to start out by defining the term self-regulatory control and try to parallel the emerging self-regulatory control in a child with brain development. Then I will go on and share some of our studies on self-regulatory control in Tourette and ADHD done by neuroimaging. At the end, I'm afraid perhaps we don't have enough time, but it would be nice to discuss on basis of neuroimaging findings, how can we facilitate self-regulation in children with Tourette and ADHD? That's why we are here. So there are many definitions. What is self-regulation? And I think we heard a good definition a couple of days ago by Russell Barkley, who said that self-regulation is any action a person directs towards their self so as to change their own behavior in order to change the likelihood of a future consequence. And I think this definition says something about that self-regulation is about modifying an automated or prepotent response, not only in children, also in adults, and it also has a temporal dimension in it. So the ability to monitor itself, the ability to think into the future are part of self-regulation. And there are many neuropsychological, many cognitive processes involved in self-regulation. And some of them are filtering, coordinating, and temporally organizing perceptions, affective experiences, memories, and thoughts. And these are just some of them. And you can just think of it like an umbrella term, which also includes executive functions. And we know that many of our patients have problems with self-regulation. Many of our patients strive with impulsive behavior, and it's not only restricted to ADHD and Tourette syndrome. But because executive functions are a very core feature of self-regulation, I would like to turn to the basis of self-regulation that probably is located in the frontal cortex. And we know that there are many cortico-subcortical circuits in the brain, and I just want to pick out two of them because I think they are fairly relevant for Tourette and ADHD. One is the frontostriatal cerebellar circuitry that also involves the anterior cingulate, and this circuitry subserves the inhibition of prepotent responses. It's involved in working memory and in the ability to plan behavior. The other one I want to focus on is the mesocorticolimbic circuitry. And this circuitry connects the orbitofrontal cortex with the limbic system, and it has also strong connections to the striatum, more to the ventral striatum. Actually, we saw a very nice picture of this in Dr. Vaccarino's talk. And these circuitries are concerned with the regulation of emotions, with decision-making, and with the control of impulsivity. So what happens during adolescence? Everyone knows what happens during adolescence. If you have kids, if you have patients, they are 14 years old, totally disorganized. They really need a lot of support from parents and from other people around them. And then 5 years later, they are able to move away from home and plan their own day. So the ability of self-regulatory control increases in many cognitive and affective domains during adolescence. From fMRI studies, we know that the brain activation gets more focused during inhibitory tasks, and this is just developing during adolescence. And then there are studies on healthy individuals, longitudinal studies that show that the cortex is sculptured during adolescence. There's a thinning of the cortex, and interestingly, the frontal cortex is the part of the cortex that is last to mature. So, having this in mind, when we turn to Tourette's syndrome and think about what is the main problem in Tourette's syndrome, everyone knows the criteria. It's motor tics and it's vocal tics. But if you look at this picture of this boy, and it's not working, but no, here. And you look at this upper row, you see that this boy seems to have a very strong urge to tic. And the urge to tic is not part of the criteria, but it's part of the clinics. And we've heard about that before today. So if we think self-regulation, the urge is probably the reason why people tic. They have the urge first, and the tic is in a way the automatic response. And this boy here is trying to modify the automatic response. He's trying to suppress the tic, but he's not able to suppress it. So he's exerting self-regulatory behavior. And if we look at the natural course of Tourette's syndrome and know that almost all the patients experience an alleviation by the end of the second decade of life, we can say that this is paralleled with the maturation of the frontal cortex. So something is happening in the frontal cortex. And there's an fMRI study that actually showed that during tic suppression, there was higher activation in the frontal and the temporal frontal cortices and the caudate nucleus. So when you think about pathophysiology of Tourette's syndrome, Dr. Vaccarino showed us very nicely that the tic generation probably in a way is connected to the striatum. But it seems that tic suppression comes from the prefrontal cortex that is exerting self-regulatory control in Tourette's. And this continuously activation of the prefrontal cortex actually leads to an increase in volume in children with Tourette's syndrome. Moreover, this increase in volume is correlated inversely with the severity of tics, meaning that if you are able to successfully activate your prefrontal cortex in order to suppress your tics, you get in a way an hypertrophy of the prefrontal cortex. Based on these findings, we were interested in the corpus callosum, because the corpus callosum is an important structure in the brain that modifies and helps to and influences the prefrontal cortex. So we looked at the corpus callosum on structural MR images in 113 children with Tourette syndrome. They were recruited from the Yale Tourette clinics. And what we found was that those children had a smaller corpus callosum compared to their controls. Moreover, we found that corpus callosum size correlated with tic severity, meaning that those who had the deviation, they had a smaller corpus callosum than their healthy peers, but they had less symptoms. And we also found that these children had a strong inverse correlation of their smaller corpus callosum and the hypertrophy of the prefrontal cortex. So this was difficult to understand. So we tried to build a model, and this model is speculative. And I hope someday maybe some neuroscientists will be able to show that it's right. But our suggestion here is, you see two different corpus callosum on these images. One has a larger and one has a smaller corpus callosum. And we focus in our model on the inhibitory function of the corpus callosum. The corpus callosum axons are glutamatergic, meaning that they are facilitatory, excitatory neurons, but they communicate with GABAergic interneurons, which are inhibitory. And we know from TMS studies, for example, that the corpus callosum has powerful inhibitory functions. So if you look at the one in the upper row, there is more connection to the inhibitory neurons, which again sends more inhibition to the prefrontal cortex, which in a way slows down the prefrontal cortex. The prefrontal cortex is not able to do the work as good as it could, so tic suppression is going down. In the other one, you see there are less axons communicating with GABAergic interneurons, giving less inhibition to the prefrontal cortex, which then enhances tic suppression. We were also able to, in a way, confirm these findings with the smaller DTI studies with 20 boys with Tourette syndrome from Norway, where we looked at the corpus callosum using diffusion tensor imaging, which is a method in MR where one is able to depict the movement of water molecules along the fibers, and this way is able to visualize fiber tracts in the brain. And you also can measure the amount of fibers or the amount of myelinization in a unit in the brain. So what you see on these actual images where you look onto the brain, here's the corpus callosum crossing a very thick fiber tract. So we were measuring something that is called anisotropy. That's the measure for the amount of myelinization or number of fibers in the corpus callosum of these boys with Tourette syndrome, and compared it to controls and found that the boys with Tourette syndrome had a general reduction in all 5 regions of the corpus callosum as measured with anisotropy, meaning that they either had less myelin or less fibers crossing. So these findings in a totally independent sample in a way confirmed our first finding from a larger structural study. So in Tourette, we know from fMRI studies that self-regulatory control in Tourette, that's tic suppression, activates the prefrontal cortex. We know from clinics and from observational studies that the ability to suppress tics evolves in pace with self-regulatory control during adolescence. And now we put in this piece of evidence that compensatory adaptive systems in Tourette result in a reorganization of the prefrontal cortex and the corpus callosum. I would now like to contrast these findings in Tourette syndrome with self-regulatory control in ADHD. It's much more difficult to define what self-regulatory control is in ADHD, and by and large, I think control of impulsivity is the core feature of self-regulatory control in ADHD. And some people might even group control of destructibility and control of motor movement under control of impulsivity. So it's about putting on the brakes. So how do they do that? They do it with the frontal cortex. And again, I would like to refer to those circuits that are important, the frontostriatal cerebellar circuitry, and an impairment of this circuit leads to behavioral disinhibition, to stimulus-bound behaviors, which are very typical for a combined type of ADHD. Whereas if you think about the mesocorticolimbic circuitry, an impairment leads to emotional instability and anxiety, typical features of the more inattentive type of ADHD. If we go to the neuroimaging literature and what is done in ADHD, there is a lot of evidence that frontostriatal cerebellar circuits are impaired in ADHD. We know that there's a reduction in volume of the frontal cortex, of the temporal cortex, corpus callosum and cerebellum, and we also know that there's a reduction in fMRI studies of the anterior cingulate activity during inference task or inhibitory tasks. When we look at the mesocorticolimbic circuits, there's very little literature done on this kind of studies, although we know that the patients suffer from problems that have to do with mesocortical limbic circuits. Therefore, I would like to present a study that we have done that concerns this circuitry. We measured the volume of the amygdala and the hippocampus in children with ADHD. And you see here a corona MR image showing the amygdala sitting on top of the hippocampus, and here you see the sagittal visualization of hippocampus and amygdala, how they sit in the brain. So why would it be interesting to study the hippocampus in ADHD? We have heard that the hippocampus is heavily involved in declarative memory, and there's no reports that declarative memory actually is impaired in ADHD. But hippocampus is also involved in executive functions, in the organizing of perceptions in general, in temporal sequencing and time perception, all features that are impaired in ADHD. As to the amygdala, the affective instability in our patient, the increased rates for affective disorders in children with ADHD and their unaffected family members, and lastly, impulsivity is a reason to study the limbic system. So we looked at the MR images. That was a structural MR study of 51 children with ADHD and 63 healthy controls, and found that there were prominent diagnosis by region effects comparing between the two groups. And it turned out that children and adolescents with ADHD had larger hippocampal volumes bilaterally. And further surface analysis, where we compared the surface of ADHD children to those hippocampi of the control children, showed that those were mainly in the anterior part of the hippocampus that is concerned with the organizing of perceptions, and which is a very plastic part of the brain, as we've heard before today. We further found that there was a correlation of volume with ADH symptom severity that was inverse, meaning that fewer symptoms were associated with a larger hippocampus. So again, the question that looks like an attempt to compensate for more basic disturbances in the prefrontal cortices and the cerebellum in the children with ADHD. Lastly, we also looked at volumetric correlations of the amygdala and the orbitofrontal cortex, because usually if you have a larger amygdala, you would also get a larger prefrontal orbitofrontal cortex, and we found that this correlation was present in the control group, but was statistically absolutely absent in the ADHD group. So the reciprocal connections between the amygdala and the orbitofrontal cortex are involved in decision making. Their interaction is important in order to learn reinforcement and to suppress undesired behavior, and lastly, involved in the control of impulsivity. So, to conclude, how do Tourette and ADHD differ? If you look at the life course of the two disorders, there's something going on in ADHD that the brain actually in Tourette syndrome is able to compensate for. So my suggestion would be that both have problems with frontostriatal cerebellar circuitry, but patients that have ADHD, and especially adult patients, seem to have prominent problems that may be located in the more mesocortical limbic circuitry, and we should go on studying this phenomenon. So as a future outlook, I hope that we will be able to map factors that help to facilitate self-regulatory control and compensation. It may actually be the same. Identify factors that inhibit such development, and this will only be possible by multidisciplinary efforts of clinicians and behavioral therapists, as well as researchers in genetics and neuroscience that may help to evaluate current and to develop new, even more effective treatment options. I would like to thank my collaborators, especially Kenneth Hugdahl in Bergen and Brad Peterson in New York, and thank you for your attention. how we time? One question? Yeah, one very short question. If not, we just move on.